Okay, let's do chapter 3 on linear motion. Motion is relative. We're going to talk about velocity and acceleration and free fall. So first of all, velocity is always described as relative to something else. So here's the sun, here's the earth. You walk on a road relative to the earth, so you have some speed relative to the earth, but the earth is moving relative to the sun. So your motion relative to the sun is different than your motion relative to the earth. And in this course, all the motion will be relative to the earth unless otherwise stated. So speed is defined as the distance covered per the amount of travel time. The units in SI units are meters per second. The equation here is speed is distance divided by time. Example, if a girl runs 4 meters in 2 seconds, her speed is 2 meters per second. 4 divided by 2 is 2. Average speed, okay, the entire distance covered divided by the total travel time. It doesn't indicate various instantaneous speeds along the way. So there's the equation for it. The example is, you drive a distance of 200 kilometers and it takes you 2 hours. That means your average speed was 100 kilometers per hour. But you may have stopped for gas or something, and you may have been speeding a little bit on the freeway for part of it. So your instantaneous speed might have changed, but that's your average speed. Instantaneous speed is the speed at any instant, and that is what is read on the speedometer of your car. So you might speed up or slow down, but whatever it says on your speedometer at any instant is this, what we call the speed, or instantaneous speed more precisely. So velocity is a description of the instantaneous speed and what direction it's moving. Velocity is a vector quantity. It has a magnitude, which the magnitude of the velocity is called the speed, and it has a direction. So constant speed is steady speed. It's not speeding up, not slowing down. Constant velocity means two things: constant speed and constant direction, so a straight line path with no acceleration. So acceleration is a very precise concept in physics. It was formulated by Galileo when he was looking at these inclined planes. He noticed that balls going downwards have the speed steadily increasing, and balls going up a hill have the speed steadily decreasing. And he had this idea that they're not accelerating if it's going on no slope. So acceleration is the rate at which velocity changes over time. It's a tricky concept. It involves a change in speed or a change in direction, or it could be both. Example here is a car making a turn. Its velocity is not constant as it goes around in a circle, and therefore it's accelerating. In equation form, the acceleration is the change in velocity divided by the time interval. And the units are whatever your units of velocity are divided by your unit of time. Example, your car's speed right now is 40 kilometers per hour. Your car's speed 5 seconds later is 45 kilometers per hour. Your change in speed is 45 minus 40 is 5 kilometers per hour. And your acceleration is this 5 kilometers per hour per 5 seconds. So you divide 5 by 5, you get 1 kilometers per hour per second. So when Galileo increased the inclination of his planes, he found that the balls roll down with greater accelerations. And when he got to a vertical incline, he got to some maximum acceleration, which is the same as if you just drop it with no incline at all. So when air resistance is negligible, all objects fell with the same unchanging acceleration. And that was called free fall. So objects falling only under the influence of gravity with no air resistance accelerate at the rate of 10 meters per second, i.e. that's the same as writing 10 meters per second squared. Or more precisely, you can call this 9.8 meters per second squared if you measure it here on Earth. So here's a ball. It's dropped off a very high cliff. And imagine if you had a little speedometer right beside the ball. Well, you'd see that this speedometer increased a fixed amount every second. So maybe the velocity started at rest if you dropped it. the equation is that the velocity will be the acceleration times the time, if the acceleration is constant. So under free fall, the acceleration is constant, 10 meters per second squared. The speed after 1 second is 10 meters per second. After 2 seconds, it's 10 times 2, it's 20 meters per second at this instant. After 3 seconds, it's acceleration 10 times 3 down here, it's 30 meters per second. It's going faster and faster, and so on. How far does it fall? The equation for that is d equals 1/2 a times t, or 1/2 at squared. So under free fall, when you have acceleration of 10 meters per second squared, the distance after 1 second, 1 squared is 1, times 10 times 1/2 gives you 5. It falls 5 meters after 1 second. After 2 seconds, 2 squared is 4, times acceleration 10 meters per second squared is 40, divided by 2 is 20 meters. After 3 seconds, 3 squared is 9, times 10 is 90, divided by 2 is 45 meters. So I find this interesting relation. After 1 second it goes 5 meters, after 2 seconds it goes 20 meters, after 3 seconds it's gone 45 meters. So as it's speeding up, the distance between adjacent dots is getting greater and greater, and so on.